Hey everybody, and welcome to section 3 of our probability course. We're going to talk about the idea of independence, and we're going to talk about inclusion exclusion. Um, so let's get into it with inclusion exclusion. First of all, we do have our standard deck of playing cards. This is the probability playground. A deck of cards is just a great toolbox, right? A sandbox kind of thing for playing around with the different ideas. And if D is the standard deck of 52 playing cards, right, we're going to have a way to identify them all. Poker players have a 2-character code that you can see demonstrated. Notice that the 10 will write as a T rather than the number 10. That way, instead of a 3-digit code for anything that's 10, it's still a 2-digit code. All right, and then you can see the entire deck written out in its 2-digit algebraic notation. And some of the subsets that we've already used and will continue to use, we of course have the suits, the spades, the hearts, the diamonds, and clubs. We also have the values. So K is the set of the 4 kings that are in the deck. Same for all of the other values, aces, queens, jacks, tens, and then the numbers also, 2, 3, 4, 5, 6, 7, 8, 9. All right. And we have the set of all red cards, the set of all black cards, and even and odd. Now, even and odd have confused some students because they didn't realize that queens and jacks and kings were even or odd. Again, and I understand that, right? We don't really attach values to them all that often. Although a queen is more powerful than a jack, and a jack is more powerful than a 10. So if you continue the integer pattern, then the jack is worth 11, the queen is worth 12, and the king is worth 13. So the jack and the king are both odds, and the queen is even. And what about the ace? Well, the ace can be either 1 or 14. It can either be an odd number or an even, right? So it's neither, right? We'll just have to agree that aces are neither even nor odd. But we can identify whether queens or jacks or kings would be even or odd. Okay, so just a couple of quick questions here. What is the probability of drawing a card at random from this standard deck of playing cards and not drawing a heart? Well, again, reminding you of the formula, the probability of not H is 1 minus the probability of H. Well, the probability of H is 13 over 52, or 1/4. 1 minus 1/4 is 3/4, right? So we have a way of doing that. And if you're following along, we can jump right over here. There's some work I need to do, hopefully, to fix this up. But in our notebook, in the UNG Data Hub, right, we can do this 1 minus 13 divided by 52 and have the right answer of 3/4, of course. Drawing a non-king red card, which is the other one here, right? A non-king red card, probability of R intersect not K. Okay. We have the probability of R intersect not K, which is equal to R throwaway K. In other words, all right, so we have all these red cards, right? And how many of them are there? Are 20 here. Let me put some hashtag, right? We have 26 red cards and we have 4 kings. Okay, so what are we doing? We're taking the 26 cards and we're throwing away the 2 that are kings. All right, so this symbol right here, our minus K, our throwaway K is what we're doing. Why? Because we have a set and we have this little piece of the set that is kings, right? And we're taking the whole set R and throwing away the kings. So it's read either R minus K or R throwaway K. All right. Um, which we can evaluate. That's 24. All right. So the probability, right, P is equal to 24 divided by 52. And you'll notice when I run this, it doesn't actually evaluate it. Why? Well, it assigned that value to the variable P, right? And then to get that as a as a real number estimate of the probability, I have to tell R, hey, display the value that's inside this variable P. Okay, drawing a red and a king. Now we are doing an intersection. Well, the intersection just means, okay, it's red and it's a king, and there are two of them, right? Not drawing an even or a diamond. Okay, so 1 minus the probability of even or diamond, which brings us what? Which brings us to the principle of inclusion exclusion. All right, let's jump back into our notes. These examples that we just did, they were on that slide. And moving to the next slide, what we're seeing is, oh, wait, we're asked about the cardinality of two sets. And the cardinalities aren't hard. Even cards, there's 6 in each suit, so there's 24 total. Diamonds is a suit, so there's 13 diamond cards. But we can't just add. A lot of people, and sadly this gets described to some people in elementary probability courses, they're like, oh, unions you just add. Well, unions are somewhat like adding, right? But we can end up double counting, right? Why? Well, as you know, there are some even cards that are diamonds, and they're right here listed for us. Okay, so this is where we're going to talk about the principle of inclusion exclusion. All right. So we just drew a line under the 6 diamond cards that are even. So they've been double counted, right? If that makes sense, what did we do? Well, we counted them once when we counted up all the even cards, but we counted them again when we counted up all the diamonds. So what do we have to do? We have to subtract those 6 diamonds back out because they've been added twice. We subtract them out once and then they're in there as they should be. And I'm sorry, I copy pasted the not equal to, and I should have changed that because this is actually equal to. Now we're getting to the right thing. I was illustrating the wrong thing here. This is actually an equal to, or should be an equal to. My apologies for that typo. Okay, so here is, for two sets, the formula for how to add the probability of the event A and the event B. Excuse me, the event A or the event B happening. Either one, either A happens by itself or B happens by itself or both of them happen. I have to add the probability of A plus the probability of B minus the intersection. All right, that's the double counted part. Okay, and you can see it pretty clearly in a picture. And again, I tend to use S for the sample space. A lot of professors use U for the universal set, the set that has everything in it. But you can see event set A and event set B is in white. And the intersection, then when I add the probability of A plus the probability of B, I count the intersection twice, so I have to subtract it out. Okay. The principle of inclusion exclusion cascades. Okay, why? Well, think about this and see if you follow, right? What do? Well, when we add H, we add this area and this area and this area one time each. And then we add E and we've added this area again and this area again and this area. And then we add F and we've added this area and this area and this area. Wow, so it's getting hard to keep track of what all we've added. Right. So let me back up and we'll talk about the double and triple counting that's happening here. And one of the reasons I put it in green is that you can see the green areas get added twice. Okay, if I look at this green area, it's going to be added once when I do the probability of H, and it's going to be added again when I do the probability of E. And notice I did A, B, and C up here. It doesn't quite match the figure. Um, but the same principle applies, right? The green part gets added twice. This green part gets added twice, once when I do E and once when I do F, and so on. So all the green parts get added twice, but every single time I add any of the sets, the purple part gets added. So the green parts have been added 2 times each. The purple part has been added in 3 times. So what do? Well, first thing I do is I have to subtract out the green parts. But notice that every time I subtract out a green part, I'm also subtracting out the purple. So what happens is in the first expression, purple gets added 3 times. In the second expression, purple gets subtracted out 3 times. So it's added 3 times, subtracted 3 times. So we have to add it back in. Okay, so the greens have to be subtracted out twice each, but that subtracts out all the purple that we had. So we have to add it back in. All right. That's what we mean by cascading. This also works with 4 sets. The union of 4 sets, where we add the 4 sets, and then we subtract out the 2-way intersections, and we add back in the 3-way intersections, and we have to subtract out the 4-way intersection that has been added in and subtracted out so many times. Okay. I'll let you play around with that. We won't need anything more than this in this course. So the formula is shown at the top there, and let's take an example. All right. So if we have the consecutive integers starting at 1 and including 1 and ending at 20 and including 20, and then we have some sets here. Sorry, we have some sets here, right? W is all the numbers that are divisible by 2, TWO. So W is all the numbers divisible by 2. T is all the numbers divisible by 3. And F is all the numbers divisible by 5. And I wasn't looking to create an acronym with W, T, and F, those set names there. Sorry, that was inadvertent. Note the cardinality of the divisible by 2 numbers is 10, right? Half of the integers between 1 and 20 are even. And then we have 6 numbers that are divisible by 3, 3, 6, 9, 12, 15, and 18. And we have 4 numbers that are divisible by 5. And I'm going to, right? So this is easy to add these cardinalities, right? We have 10 even numbers. We have 6 numbers that are divisible by 3. We have 4 numbers that are divisible by 5. And it's like, look, do we have all 20? Well, no, we don't. Why? Well, if you look, right, I have 3 even numbers, right, in the set T, right? So I have to subtract those 3 out, and you can see it here, right? And then in T and F, divisible by 3 and divisible by 5, I have just 1, right? And then when we have divisible by 2 and divisible by 5, actually there's a, excuse me, yeah, even numbers divisible by 5, right? Well, we have 2 of them. We have 10 and 20, right? So we've added them all in. We've subtracted out the double counting. We have to add back in the ones that are even and divisible by 3 and divisible by 5, which is what? Well, there's none like that, right? Okay, so we add them all in. We get 20. We subtract out 6, and we add nothing. So 20 minus 6 is 14. Okay, and then to check our work, I have highlighted with the bold text all the things that aren't in any of these 3 sets. Okay, and there are, as you can see, 6 values, 1, 7, 11, 13, 17, and 19 that are not in these 3 sets. So 14 is indeed the correct answer. And let me apologize for that flicker. I hit a stray button in my recording software, so we had a couple seconds of downtime and flickering screen. Sorry about that. You can see that on the notes page in the Data Hub, I did do all of these sets, so you can make whatever notes you need to here. And that's going to wrap it up. So we do know how to deal with intersections. Intersections are easy. You'll see in a moment if the intersections are empty, then the events are independent, and it's a lot easier to add them or subtract them, right? It's when they have this non-empty intersection that it becomes a problem, and not with intersection, but with the union, right? And we've learned how to do that. So we'll look at independence in the next part of this video.